What's up, YouTube? In this video, we're going to be looking at building our own custom data structure. I'm going to start with giving you the requirements, business/technical requirements, and then look at some of the unit tests required in order to satisfy these business requirements. Then look at a bunch of implementations for this requirement, and then benchmarking of these requirements. That's the sort of the progression. There's different chapters. The idea of this video is you can stop at any point in time, go do your own implementations, and then join back in based on the chapter markings. I'll have the full source code of this project, the solution, the completed solution on my GitHub. So it won't be the progression, but just the completed version of it. So you have access to look at the parts and pieces that you need help with. But the idea is that you can understand the requirements and then go do your own thing, the unit testing as well as the implementation. Or you can say, okay, I need some more help with the requirements. I'll go to the next chapter where I go a little deeper in the requirements. The next chapter, I talk about some of the unit test scenarios and expectations. Then I talk about the implementations, and then I talk about the benchmarks. So that's the progression. I'm hoping that this would encourage you to actually have your own implementations. If there are enough implementations, or you feel that your implementations can be as fast or better than what I might have, then you can send me your code via GitHub or a gist, and I can include that in my project and do the benchmark for, have like a shootout, if you will, in another video for that. That might be interesting. The requirements will also be in the way of sort of language, English, and then also I'll try and explain that via a database, data model. For those of you who are more familiar with the database side and would find it easier to understand requirements by presenting, I'm going to be presenting two data models. Now, if there's interest in the database side of things, I don't have many videos or any video for that matter on my chapter with regards to databases. So if there's an interest in that, then we can use this implementation, if you will, in a separate video where I talk about my ADO.NET code and my database and stuff like that. So if you are, please let me know in the comments. All right. So without further ado, let's go into the requirements. This is a data structure that is required in many business scenarios. It's not something that's available out of the box from in .NET. However, we will be using a bunch of other data structures that are available to us in .NET by default, and using a composition of these data structures produce the data structure that we require. How? I leave that up to you. I have my own implementations. I've got 4 implementations. You could try your own. I'm going to give you the requirements first, and then you can break away from me, as I said, and go back and join in. So there'll be time code links in the description below, and of course the link to the actual final project. So the requirements. All right. So as you can see here, a few requirements are, the keys are unique. So you can imagine a data structure that has a key and values of one to many. So imagine a data structure that has a mapping between a key and values, one key to multiple values. It's kind of like a dictionary, but not quite, right? And this one key can be mapped to multiple values. The keys are unique. It's kind of like in a dictionary, the key is unique. The values are also unique. So the same value cannot be mapped to multiple keys. So I'm going to make this a little more concrete. This data structure would be used where you have, let's say, rules that are associated to states, or messages that you display in your UI that is associated to states, and so on and so forth. So I'm going to use messages because it's a string. But it's not limited to string, right? So it could be anything. But for this example, I'm going to use messages as the key and the states as values. So a message can be associated to multiple keys. Messages are unique. You don't want to repeat that message over and over again and find out that you got 2 different versions of it, and then they go out of sync and all that. So the way you see this from a database, not database, I don't mean database. A business perspective is these messages are unique, and these messages are associated to multiple states in this case. The states are, of course, unique. You can't repeat the same state. You can't have the same state being associated to multiple messages. So you want a data structure that allows you to store this information in this fashion with all the constraints in place, with all the, with all the constraints in place, so that the data structure is handling that aspect of the requirement as well, kind of like a database. Now, unlike a dictionary, this data structure has to be able to search by value, which is given a value, find the message, given a state, find a message. right? So it's backwards, even though the key is the message and a key is associated to multiple states. At runtime, when you're using this structure, you're searching by state to get the message, right? And that's where the rub is. And this is the difference. This is the reason this kind of a data structure exists, and this is the reason that this video exists. I'm hoping you can understand or see where you might be able to use this data structure in your own applications, because it's a very common concept, a very common need in business systems. All right. So I'm going to list out the requirements. And if you get this, you can move on and start doing your own implementation. If not, the next I'll be doing is using a database. I'll explain the requirements using 2 different data models, and hopefully that'll help you understand the requirements and start your implementation. Okay. So as I mentioned, the keys are unique. So let's say the messages in our case, the keys are unique. The values are also unique. So in this case, states, they're also unique. By unique, I mean you can't repeat the same state in that data structure. Then a key can have multiple values associated to it. So that is, a message can have multiple states associated to it. Given a value that has been associated to a key, should return the key. So given a value, given the state, return the key. If the value was not found, it should throw an exception saying value not mapped to a key exception. Should allow associating a new value to a pre-existing key. Now I need to show you the API. There's an interface that I've defined, and all my implementations implement that interface. So I should show you that interface so that you understand why some of these requirements exist. All right. So let me switch to the Visual Studio code here. Okay. So here's the interface that you're going to be implementing as well. I'm hoping that you will implement this as well multiple times, different styles, different ways of implementing the same interface to satisfy all the requirements. This is generic, by the way. If you're not familiar or not comfortable with generics, then just assume string key and string value, right? Don't worry about the generics part. Don't get hung up on that. Just say it's a string. So now to define the generic types, you just say my key is going to be a string and the value is going to be, in this case, an array of strings. All right. So just ignore the generic parts. There's a property, an indexer property. You know how when you use the square brackets, that's called the indexer property. And this indexer property will ask for a value. It'll return a key. So this is the typical way in which you would use this data structure at runtime. You to access the message you're looking for, given the state, get back the message. It's going to be using that indexer property. So that's the definition here. To add the data into the data structure, you have this one method that says add one-to-many mappings. Given the key, so let's say a message, give me and the multiple states, it should allow you to make that association for this message to that state, those states, right? So if you remember this API, then the requirements will make more sense. So there. All right. So now we move on to the next requirement here. Should allow associating a new value to a pre-existing key. So imagine you've already added a message and associated to multiple states. And now you want to associate another state to the same pre-existing message. Right? So that's what it's saying. Should allow associating a new value to a pre-existing key. So even though the key exists, you can still call the method with the pre-existing key and a new set of values, one or more new values, that non-existing values, and it'll make that association to the pre-existing key, which is fine. The next requirement is associating a value that has previously been associated to another key should throw. So if you're trying to add a value to a whole other key, and that value pre-exists because the value or states in this case are unique, you can't do that. It's going to throw an exception saying value has prior mapping to key exception. All right. And then when one or more values have been associated to a pre-existing key, then association should remain unchanged. So in other words, you're using this method to add. You're saying here's a key and here's a value. The key is unique. It's different. It's a new key. It doesn't exist before. Of the values, one or more already exist, or the associations to another message already exist, state to message. If that's the case, don't touch the data structure at all. As in, don't try and create the new key with the values that are unique and then sort of skip the rest, right? It's like a transaction, all or nothing. So when you call this method, it's an all or nothing. If it's completely successful, great. If there's any problem, the entire thing sort of rolls back, if you will. Right? That's the requirement there. That's the last requirement. And it throws another exception. called value has prior mapping to key exception. All right. In my mind, this is enough to get started. If you understand requirements and you're comfortable with all of the programming and kind of getting started from scratch, this is good enough. I suggest go forth and conquer. All right. For those of you who need a little more help, I'm going to now re-explain the same requirements by way of 2 different data models. Maybe that'll help you grasp the requirements even better. And there's no database code. It's just a data model and kind of diagram. I'm going to explain that, and hopefully that'll help you with that. So if you don't feel comfortable with the requirements so far, then stick on and I'll go to the next step. So the next step is a database. So imagine you have a table that has a message. There's an ID column and there's a description column. The ID is the primary key and the description has a unique index in it, which basically means that the same message cannot be in this table more than once. So the messages are unique, right? We know that's a requirement. And then there's a detail table or a one-to-many association between the message table and the state message table, where again, there's an ID column. That's the primary key of this table. The message ID is a foreign key. So that's this ID column of this table. So it's called message ID, and this is the foreign key. And then there's an acronym that is the state acronym. And that's also got a unique index on it because we know the values also need to be unique. So this data model will support the requirements with regards to being able to insert data and block you if you make a mistake, right? Now this is a header detail relationship. The next version is a association relationship. So it's a different style. They both have the pros and cons. Both are valid. And I'll explain to you at the end which one is for what reason or why would you use one or the other from a database standpoint. All right. The other way to do this, the other data model would be that there's a message table. So this table is not changed. The ID is the primary key. Description is a unique index on this table. We have a state table as well, where the ID is a primary key and the acronym is unique index. And then there's an association table that associates these records from these 2 tables into another table. And this table has a message ID, the foreign key from here, and the state ID, the foreign key from there. But the state ID has also got a unique index on it. And the combination of these 2 is the primary key. In other words, you can't have the same state message ID and state repeated in this table, right? So that's the primary key will ensure that. But if the state is associated to a whole other message, you can't have that either because, again, the value is unique, right? Now, you would use an association style data model when the 2 entities, in this case, the message and the state, are independent of each other, meaning, let's say in your system, the message already exists, it's already there, you need that message for whatever else. And of course, states already exist, they're used in so many other places in your system. They pre-exist. They can exist independent of the other. Then you build an association rather than a header detail, right? However, if the detail has no business existing by itself, like an order and order details, there's no order details without the order header, then it doesn't make sense to have the order details. But if that's the only reason order detail exists is because of the order, then maybe a one-to-many parent-child or header detail relationship is the better relationship, if not the association one. All right. Continuing on with the data model side of things, I have a implementation of the database with inclusive of the stored procs and the views and all of that. So we'll take a look at that. But of course, there's a time code. If you think you want to just skip over to the next part, next chapter, please skip over to the next chapter. If you think you got enough information already to go and do your implementations, then off you go and do your implementations. You can join back in the next chapter. All right. So I have this one-to-many database here. I've used the association data model. So you can see I've got these. Let me just zoom in here. You can see it better. Okay. So I've got the message table, the state table, and the source message state table. So this is exactly like the second data model that I talked about in the presentation slide. All right. And they've got the proper indices and primary keys set up for this. Then I have a view that I've defined called view state message. This essentially does the join. So if I look at the view, it does the join. Oops, there. So it essentially joins the three tables to produce the view. This is not about the database itself. I'm assuming you're familiar with databases. If you're not and you would like to understand a little bit more and to dig deeper, let me know in the comments below. And then I can have a separate video talking about the same problem statement and have a full-blown implementation in C# as well through using AD.NET and building out the database from scratch. So if that's an interest, let me know in the comments and I can do that video separately. Okay, so the view essentially, as I said, just does the join, right? So it joins up these tables here. And then I have a stored procedure that executes or can use the view. So if I modify the store proc, you'll see the code for that. It given a state acronym, so we are searching by state. Given a state, it'll use the view and pull out the description of the message. Right? So that's what that is, the database implementation. All right. So end of, I don't know what chapter this is, but next we're going to be looking at the unit test. Given the requirements, what should the unit test be? The scenarios and the expectations. I won't show you the implementation because the source code is available. But for those of you who don't want to see the implementation, you want to just hint at like, how do I get started and what the methods in there and what the scenarios and expectations should be for the unit test, then stick around. I'll just show you the method signatures, but not a whole lot more. And also show you something in the way of, because I have multiple implementations, I want the same suite of tests, methods, to be executed for the different implementations. I don't want to write the same test over and over for the different implementations. So I have something in the unit testing project that will help you understand or do that as well. All right. So if you look at our project and look at the unit tests. Okay. So I've collapsed this all to just the definitions, method definitions. So this is the one method, the first method. So when provided with a value that has been mapped to a key, returns the key. Right? When provided with a value that's been mapped to a key, returns the key. That's one scenario and an expectation. The next scenario is and this is the indexer property. So both of them are, in this case, are testing the indexer property, as you can see from this part here. When provided with a value not mapped to a key, throws. That's the scenario and expectation. That lines delineate the method name, scenario, and expectation, the three parts. This stuff here is actually helping me run the same test multiple times for the three different types of implementations that I have. I'm not going to explain how this works in the video, but you can certainly look at the code and understand like how is that done and then implement your own. So that way you can use the same suite of tests for all implementations that you might have in the future without having to write the same tests over and over again. All right. Okay, then for the indexer, there's these two scenarios. Then for this method, the add one-to-many mapping, there's 4 scenarios. So let's look at what those are. When adding a new value to existing key, should map value to the key, right? So even though the key is existing, the value is not, it should add it. When value has prior mapping, throws, right? We know that if the value pre-exists in the data structure, then your data structure should throw a very specific exception with a very specific message. When one or more values has prior mapping, mapping remains unchanged. So not only does this throw the exception, but it also, remember, it's like a transaction. It's an all or nothing. So you want to make sure you can test that and that's exactly what the data structure does and doesn't do something else. It doesn't change the data, for example. And the last scenario is when key exists, should add values to existing keys. Right, when key exists, should add, yeah. So if the key is there with other values, but you're now calling this method again with the same key, with the pre-existing key, but a whole different set of new values, then it should just add new values to the pre-existing key. It should not throw an exception, right? All right, so that's you can look at the source code if you need help with the kind of getting started with the unit tests. Look at the source code, kind of just see the parts that the bare minimums you feel like you actually achieve something on your own so that, you're not feeling like you just copy paste or something. So I'll leave all that up to you. The entire project, as I said, the completed version is available. So you're going to have to be judicious in what you pick and choose to see and not see at your own convenience. All right. So now going on to the next chapter. I'll put the links in the description below. So if you want to move off and do your thing and then come back and join us in the next chapter, do that. If not, continue watching. I'll move on to the next chapter. The next chapter are my implementations. The two data models that I presented to you are actually the way I've implemented the 4 different implementations I have in my C# course. I'm not using the database, but I'm using conceptually the same idea where I've got 2 tables and there's an association, or there's 1 table and a one-to-many, and the sort of an association or one-to-many between 2 different in-memory data structures. So I'll start with the one-to-many. There's 2 implementations of that, and then there's 2 implementations of the association type. So if I look at my data structures here, as you can see here, I have the interface, and then I have a data table version of this implementation. Let me zoom out here. And for those of you not used data tables and things, the data table is like a table. You can define primary keys, indices, all that sort of thing, foreign key constraints. And a data set is like a database. You can have multiple data tables that are all in some form of association, right? They're beautiful classes. I love using them. But most people don't even bother touching them. So I thought maybe why not try that and see how that works, right? So effectively, I've got the 2 tables, the key data table and the value data table. And then I got a relation type. This is very specific to data tables, the way they're implemented. But here's essentially the schema. All of this. So I do that in the time of construction. I create data table, that's the key. It has these 2 columns, the ID and description. And then there's a primary key for the ID column. And then there's a constraint for the second column, the description, which is a unique constraint. All right. So think of that as the header table, and then the detail table is the value table. You can see that here. It's also got 2 columns, the value column and the key ID column, which is like a foreign key, if you will, from this table. And the primary key is the value column. Right. This is the primary key. That's the value column. Then there's a foreign key constraint that takes on the ID column from this table as a foreign key constraint for this one. So this key ID is nothing but the key ID. The key ID. That's why it's called key ID. All right. And then that sets up the relationship. So this is all stuff you just have to do when you're using data tables and setting up primary keys and indices and all this. Very much like you're setting up a database, but in memory, if you will. And then I've got the implementation. This is all generics. As I said, if you are not comfortable with generics, just assume string for the key and string for the values. And don't worry about the generics at this point. All right, so I won't go into the implementations, but I just want to describe the different implementations I have in my project. The next implementation that's similar to the one-to-many, like the one-to-many, is this one-to-many map list. This is using a list of T, and it's got these 2 different lists internally that are house the keys and the key value mappings. Again, as I said, this is like the one-to-many model that I showed you in the database. Again, I won't go into the implementation. In case you want to have your own implementation, try your hand at it. All right, then the next one is the sorted list. So the previous one was a list. This was a sorted list implementation. So what's the difference between a list and a sorted list? The list is essentially an array behind the scenes. A sorted list is a sorted array behind the scenes. In one case, in the sorted list case, it would use a binary search algorithm to search for something you're looking for. In the case of the list, it's going to be just an iterative process going from, it's an O(n) operation, if you know the big O notation, whereas with the sorted list is a O log n operation, right? This will be interesting to see in the benchmarks. So if you're wanting to take a guess what's going to happen, you can, watch the next part as well, because in the benchmark, there are a few surprises, not necessarily surprises. I mean, I was sort of expecting it, but it's surprising just to see some of the results, and then you can sort of reason about why the results are the way they are. All right. So that's the association model. So the 3 tables, if you will. So that's the 3 lists. Each list is doing their own little part, and there's this understanding of an association between these 3 lists. Unlike a data table I showed you before, you can't build in the foreign key constraints and all that in this. So you have to do it, kind of manage it yourself. And the final implementation is the using 3 dictionaries. So again, it's an association model, if you will. And it's using 3 dictionaries. And then the dictionary, of course, has a big O of O1. So it's constant time. That's not to say it's fast. It just says it's constant. Whatever the time is sort of kind of constant, right? So we'll see in the benchmarks what the outcome of these 4 implementations is and which ones are kind of better than the next. And this, I've got benchmarks across different numbers of items in these collections. So maybe there's a change as the number of items increases because one is an ON operation, one's an O log N operation, one's an O1 operation, right? So I've shown you 4 different implementations. I hope that's inspiring. You can try your hand at all 4 of those without looking at the implementation. Just work on the idea. If you've got your own ideas about how you might be able to use some pre-existing data structure or make a whole other data structure in whichever way that satisfies the requirements, go right ahead. And then we'll have a shootout. Or you can describe to me what it is you did, and I'll try and implement that myself. Really, the idea is to encourage people to kind of try their own hand and have this interaction, where you can send me stuff and I can try that out and we can have a shootout. It'll be a lot of fun. All right. So that brings us to now the next chapter, which is the benchmarking part. All right. So let's look at the benchmarks. So here we have the benchmarks. The numbers here are the number of items in the collection, in the data structure, and the 10 is the number of matching. So when you're looking for stuff, you want to make sure that there's at least something that's found. The stuff that you're looking for, there's 10 things there that have potential matches. Same here, there's 100 items in all, but only 24 of them you'll be matching on. And then there's 200 items of which you'll only be matching on 40. I'm not sure where these numbers came from. I don't remember how I picked the numbers, but maybe it was just random and it happened to be these numbers. It's just a way of saying that when you're looking for stuff, 40 of them you'll find matches for and others you won't. And so there's some sort of relationship there. The data table one is the first one here. And then, so you can see for 50 items, the data table implementation is the slowest and the dictionary implementation is the fastest. And the list implementation is second fastest. And you can see from the graph here, they're all one on top of the other. This is in microseconds, the timings over here. And as the number of items increases, you'll find that this, I don't know why this is going to 126 here. That's weird. It's come back down to 11. Then it's gone back to, wow, I didn't notice this 11 then. There's something wrong with this 11. It must have been 126, but then I must have mistyped this over here. So it kind of seems to have gone down. I'll have to check that again. But nonetheless, as we increase, you can see that the map list, which is an array, so it's an ON operation, which means the time will increase as the number of items increases, and which is what's happening. So you can see the time is increasing. And there'll come a point where, as you can see here, the sorted list is slower than the list. Right? The sorted list is slower than the list. Why is that? See if you can explain that to yourselves. Got it? Okay, I'll try. I mean, I'm not confirmed this, but I'll try it myself. They're both implemented using array. One is searching using a binary search. One is searching using just brute force, just kind of iterating through the array and finding a match. So you can imagine the ON operation, of course, will be getting slower and slower. But how come the binary search is not faster than an ON operation, no matter what the number of items in the collection? This is a key aspect people need to understand. Arrays are actually blazingly fast, and not just C# in almost every language. It's the data structure of choice for performance. It is the data structure of choice for performance. Now, because there are many implications to that. Arrays are contiguous in memory. Now, in C#, unfortunately, when you have an array of reference types, the pointers to the reference types are in contiguous memory. The items themselves are not. In C++, you could say, I want my array to have even the references in line inside the array itself, rather than just pointers to that. So in the C++ world, arrays definitely are the data structure of choice for performance. In C#. For value types, certainly they're all in line, but for reference types, only the pointers are in line. So the way I'm thinking, or the reason I'm thinking that the binary search ends up being slower with smaller numbers is essentially at the hardware level, the caching, CPU caches. It's possible that when you're doing a binary search, you're kind of jumping, all over the place, right? You're not running through in one sequence. So the prefetcher it's probably misfiring. In other words, it's prefetching this thing, but you see you want to go here, then it prefetches the next one there. You say want to come back here, and so on. So it's possible that you're confusing the prefetcher, the branch prediction, and all of that fancy hardware features we have. And so the array is outperforming a binary search. And then there comes a time where the n, the number of items in the array, is in fact causing the slowdown. And now the binary search can actually become a little faster. So you can see here, yeah, with 500 items onwards, the array is slower than the binary search. Of course, the dictionary is almost a constant time. Let's look at the data table thing. So the data table thing is sort of keeping in step with the sorted list part, right? So they're almost very close. And you can see as we move on, the data table one is always just very close to the sorted list. So in other words, you could almost imagine that the data table has implemented the search also using a binary search. That whole indexing and foreign key constraints and all that are just the sort of the rules, but it's basically searching using a binary search. So you can see that from the graph here. Now the graph, this hockey stick kind of thing going on here is only because of the fact that it goes from 900 to 1,000 to 2,000 and 3,000. So it's not kind of like on the same scale, right? So I don't think it suddenly got worse. It's just the fact that it went from 1,000 to 2,000 instead of increments of 100. It's jumped to an increment of 1,000 here, and then another 1,000. So the orange and the, what line is this? Gray, blue, the blue. The data table and the sorted list are almost neck and neck here. I mean, not almost, they are neck and neck. The dictionary is just a flat line, seemingly flat line. You can see the numbers are actually just changing. It's not really that constant, but in the scheme of things, they are. And the data, the array, the list, it's just a linear increase in its ON. So as the number increases, the time increases in a linear fashion. The interesting / disappointing part is that this data table has a lot of memory allocations and also Gen 0 collections. 164 Gen 0 collections per 1,000 iterations. That is insane. I've not seen such a large number. I cannot imagine why, for the sake of searching, this data table has to make so many allocations and therefore is causing so many garbage collections. I don't know. So that's definitely the sad downside of using data tables. Even though they're in memory, that's not a good idea given that that's what's happening with the allocations and the garbage collections. So that brings us to the end of this video. I hope you've enjoyed yourselves. I hope you learned a few things. If you have, please give me a thumbs up. And I will see you next time.